Welcome back. This is the fourth segment of section 2.1. I think I'll probably be able to finish out all the textbook material in segment 4, and possibly even the supplemental material that I wanted to do, but that may take a little bit longer. And so I may just add that as kind of a fifth segment that's just a single proof. It's not something that's necessarily required out of the course, but it is kind of an interesting sort of exercise in some algebraic techniques. But what we're going to do in this segment is we're going to look at some very specific triangles to elicit the values of the trigonometric functions based on, opposite over adjacent, that sort of thing that we developed last time for the angles 30 degrees, 60 degrees, and 45 degrees. Now, like I said, in the next, if I can squeeze it in, I'll do 18 degrees, really just the sine of 18 degrees, but that may be reserved for another segment. So anyways, let's move on over here, and I'll give you the basis, sort of the setup of what we're trying to do here. So this is section 2.1. Now I think we're on page 7. So it turns out that to be able to find values of trigonometric functions, you have to kind of start somewhere. And since trigonometry is very much rooted in geometry, we're going to start with a geometric idea. So before I do this, I want to do something called the base angle theorem. And I'm going to do it without proof. I mean, we can. Well, I mean, it might be worth it. I'm not so sure. I mean, these videos can get kind of long, but basically, here's the idea. The definition of an isosceles triangle is one where two sides are equal. Now, it could be sort of a sort of top hat or a witch hat looking one like this. It could be flat, whatever. It doesn't make any difference. What the requirement of an isosceles triangle is that these two sides are equal. And the third one can be anything at once. It could actually be an equilateral triangle. Now, the base angle theorem says that if you have an isosceles triangle, then the associated angles, which are called the base angles, because if you think of it, it's like it's the base times the height. It's kind of where that term comes from, that these base angles are actually equal as well. So I'll just state it. The base angles of an isosceles triangle are congruent. And this might be something that possibly you proved in a geometry class at some point. But I'm going to use this result, and I think it's sufficient to just do that. So now I'm going to construct an equilateral triangle which, remember, the definition of an equilateral triangle doesn't have anything to do with the angles. What it tells you is that the sides are all the same. And so what I'm going to do is I'm going to use a very specific one. I mean, we can scale them up and down because of the fundamental theorem of similar triangles. But I'm going to say that each side has a length of 2, and it's just because it makes the arithmetic a little bit easier in the end. So the first thing that I want to do is I want to prove to you that all of the angles are the same. Remember, just because it's an equilateral triangle doesn't mean that it's that the angles are necessarily equal as well, but it does turn out to be the case. So I want you to think for a second. These two sides are equal to each other. So this is an equilateral triangle. And therefore, by the base angle theorem, this angle is equal to that angle, right? So this angle equals that angle. Now, looking at it from another perspective, these two sides are equal. Therefore, it is an isosceles triangle, and the base angles have to be equal, right? So this angle equals this angle, or the measure anyways. This angle, the measure of this angle equals the measure of this angle. The measure of this angle also equals the measure of that angle. Equality is transitive, so they're all equal to each other. We have three angles that are all equal, and they have to add up to 180 degrees. So therefore, they all have to equal 60 degrees. And so we can kind of use that result now. 60 degrees, this one up here also happens to be 60 degrees. But what I'm going to do is I'm going to bisect, rather than labeling, I'm going to bisect this angle up here. Okay. So I split it in half. I know it's 60, the whole angle is 60 degrees. So that makes this one up here 30 degrees. And that makes this one a right angle, right? Because 30 plus 60 is 90. The whole thing has to add up to 90. So this is 90 as well. And you've got two basically congruent triangles, right? Because you can pick any version you want. You've got angle, angle, side, angle. You've got angle, angle, side. I mean, any kind of way you'd like to do this. The triangle on the left is congruent to the triangle on the right. They're just mirror images of each other. And therefore, these split distances are equal. So the angle bisector happens to be the bisector of this line as well. So if we just look at the left-hand side, we can say that this length is 1. Okay, so now I'm going to take that triangle, put it over here to the right, kind of just blow up a portion, just the right triangle. We know that that side is 2, this side is 1, and applying the Pythagorean theorem, we can find the third side, right? So what's the Pythagorean theorem tell us? It tells you that this number squared plus whatever this number is squared equals that number squared. Or alternatively, this number squared minus that number squared is equal to this number squared. So if 2 squared is 4, subtract 1 squared, 1, which is 3, is equal to this side squared. And so therefore, this other leg is equal to the square root of 3. And I'm going to label the angles. So we have created one of the first sort of primary triangles used to establish the values of the various trig functions for things besides some sort of quadrant angle. So sometimes people find this to be difficult to memorize because it has a radical in it, I guess. I don't know, but these are pretty easy triangles because it's 1, 2, square root of 3, 1, 2, 3, right? It isn't 1, 2, 3, but I mean, it's a quick way to remember that a 30, 60, 90 triangle has this 1, 2, 3 buried in it. It's easy to count. So, but based on this, we should be able to find the sine of 30 degrees. And I won't bore you with all of them, all 6 of them, but the sine of 30 degrees, looking at this angle, is the opposite over the hypotenuse, right? Opposite over the hypotenuse. This is a right triangle, so I can use that SOHCAHTOA is 1/2. What about the cosine of 30 degrees? Well, the cosine of 30 degrees is, well, here's the 30, so it's adjacent over hypotenuse, 2, and then the tangent is opposite over adjacent. So tangent of 30 degrees is equal to 1 over root 3, which we know needs to be simplified to square root of 3 over 3. And of course, if you wanted the reciprocal functions, cosecant would be 2, secant would be 2 root 3 over 3, cotangent would be square root of 3. Now, how about the 60 degree angle? So sine of 60 degrees. Well, I mean, we can do this in a number of ways. We know that these are cofunctions of complementary angles. It's got to be the same number, but let's just make sure that that's what we get. Sine of 60 degrees is opposite over hypotenuse, which is in fact the same as cosine of 30. Similarly, cosine of 60 degrees is 1/2. And the tangent of 60 degrees is opposite over adjacent, square root of 3. Okay, so there's a table in the book that has these values. You could certainly go through and write what it is for all the cofunctions and everything else. Now, again, as I mentioned in the previous chapter, I'm like, you have to memorize this stuff. I don't know that I will try to show you some ways to remember them, but they don't necessarily work for everything. So straight memorization is also helpful. I would suggest that as you're studying in chapter 2, that you again create some flashcards, with the specific trig function and angle, and then have the value on the back and test yourself and make sure that you remember what it is. That skill does have value as you go on. So, but just to make sure, let's just try one. How about what's the secant of 60 degrees without looking at a triangle? Well, okay, so the secant of 60 degrees we know is by the reciprocal identity is equal to the cosine, the 1 over the cosine of 60 degrees. Now the cosine of 60 degrees is 1/2. So 1 over 1/2. So the secant of 60 degrees must be 2. Let's check to make sure that that's right based on the triangle. So remember, secant is not adjacent over hypotenuse, it's hypotenuse over adjacent. So here's your 60-degree angle. Hypotenuse is 2, adjacent is 1. We do get the result we were looking for. Okay, so that's the 30, 60, 90 triangle. Let's go on to another one here. So section 2.1, I think we're now on page 8. Okay, so what I'm going to do is I'm going to create an isosceles triangle that actually has a right angle at its apex. So this is the archetype here. And for simplicity's sake, I don't have the same reason to make it 2, make it 1. In the previous example, it's because I didn't want to mess with a bunch of fractions. But anyways, so here's an isosceles triangle, just happens to have a right angle at the apex. Now, by the base angle theorem, that means that these two angles, the base angles, are congruent. And because they're congruent, they're equal. So something times 2 plus 90 is equal to 180. So these two are equal to 90, and they're both equal to each other, so these must be 45 degrees. Okay, and they're both equal to 45. It's a right triangle, and we know the length of the legs, so the hypotenuse is equal to the square of 1, which is 1, plus the square of 1, another 1, so the sum of those is 2. So this opposite, the hypotenuse here, has to be equal to the square root of 2. So that's just a real quick geometric proof, which I didn't write all the steps down, but of course you could. That gives you the angle. We solved this triangle, so to speak. I have every angle and every side, and it happens to be a right triangle. So now I can start talking about what the trig functions are. So it doesn't really matter which angle you pick. The sine of 45 degrees, let's just pick this one, is opposite over the hypotenuse. So that's 1 over square root of 2, which simplifies to square root of 2 over 2. Similarly, cosine of 45 degrees, well, cosine's adjacent over hypotenuse. It's the same number. So 1 over square root of 2, which simplifies to square root of 2 over 2. Oh, sorry, square root of 2, not over square root of 2. Square root of 2 over 2. Okay, so what about tangent? Tangent of 45 degrees. Well, that's opposite over adjacent, 1 over 1. It's just equal to 1. And to finish them out, we'll just go ahead and do them all. So cotangent of 45 degrees happens to be equal to the reciprocal of tangent, which is just 1. The secant of 45 degrees happens to be the reciprocal of cosine, which is just square root of 2. And cosecant of 45 degrees happens to be the reciprocal of sine, which is just square root of 2. So here you now have all of the values for all of the trig functions for 45 degrees. This is starting to look like a lot of stuff to remember. I agree with you. So what I'm going to do is I'm going to show you a little trick. Okay, I'm going to hold out my hand here. So every finger represents. I don't even need my. I don't really need my thumb. Every finger represents an angle. So this is 0 because I have 0 fingers up. This is 1, which represents 30 degrees. Right, 30 degrees. The next highest angle I have is 45 degrees, 60 degrees, 90 degrees. Okay, so 0, 30, 45, 60, 90. All right, now here's the trick. Take the number of fingers associated with that angle that's sticking up. In this case, it's 0. Take the square root of that number. In this case, it's 0. Divide that number by 2. In this case, it's 0. The sine of 0 degrees is 0. Okay? Next, let's look at 30 degrees. I have 1 finger up. The square root of 1 is 1. Divide that by 2, I get 1/2. The sine of 30 degrees is 1/2. 45 degrees. I have 2 fingers up. The square root of 2 is just simply the square root of 2. Then divide that number by 2. Square root of 2 over 2. That is the sine of 45 degrees. Okay? Next one, 3. 3 represents the angle 60 degrees. The square root of 3 is just simply the square root of 3. Divide that number by 2. The sine of 60 degrees is equal to square root of 3 over 2. Finally, 90 degrees. I've got 4 fingers up. The square root of 4 is 2. Divide that number by 2, you get 1. The sine of 90 degrees is 1. Okay, so this is a quick way to remember the values of sine for the acute angles. 0, 1/2, root 2 over 2, root 3 over 2, 1. Now, if you're wanting to do this for cosine, because cosine is the cofunction, you just do it backwards. You say, okay, that's 0, that's 30, that's 45, that's 60, that's 90, and you get exactly the same results. But I don't have a quick, easy, cheesy way to do that for tangent, but at least it'll get you somewhere so that you can start making some relationships between these. So this is the end of the material for section 2.1. I am going to put another supplemental video on there, and I may not do it right away, but I'll get it out there at some point. That is the derivation of the sine of 18 degrees, because I think it's an interesting algebra problem. But I won't bore you with that. If that's something you'd like to see, it may be something that I refer to much later in the semester, but it won't be anything that's super critical. So in the meantime, I will see you all.